Hello and welcome to the EnvirotechOnline podcast, where we explore the trends, technologies, and transformations shaping the world of environmental monitoring. I'm Jed Thomas, editor of EnvirotechOnline.
And I'm Alan Booth, senior editor here at ILM Media. Today we're talking about carbon capture, but not in the way it's usually framed.
That's right, the conversation is shifting. Carbon capture and utilization, CCU, is no longer judged just by how much CO2 you can strip from a flue gas stream. Increasingly, the real question is, how clean is that CO2 once it's captured?
Because if your carbon dioxide is heading for greenhouses, synthetic fuels, or the drinks industry, purity suddenly becomes everything.
Exactly, and that's where a recent report from the EU-funded SCOPE programme comes in. The study looked at a pilot capture plant at Twence's waste-to-energy facility in the Netherlands, capturing around 500 kilograms per hour of CO2 from incineration flue gas.
Incineration, not the easiest feedstock when it comes to contaminants.
No, it's a tough one, but the team wanted to find out, can this CO2 meet beverage grade standards, the kind you'd need for use in food, drinks, or greenhouse agriculture?
So what did they do?
They installed a Carboscan 300 analyzer, normally used in the beverage CO2 supply chain, and ran it continuously at 2 points, just after production and at the tank outlet before dispatch.
And what did they measure?
They measured everything the European Industrial Gases Association recommends in DOC 7017. That includes moisture, oxygen, carbon monoxide, sulfur species, hydrocarbons, aromatics, aldehydes, ammonia. Basically, every trace gas that could compromise downstream applications.
What's interesting is how operational changes show up in real-time monitoring, isn't it?
Absolutely. The report shows that adsorption column switching, when done based on dew point alone, led to irregular spikes in methane and other volatiles. But when they changed to time-based cycling, those spikes disappeared.
So monitoring isn't just for compliance, it becomes a feedback tool.
Exactly. Moisture dropped from under 5 parts per million to consistently below 1 parts per million after process changes. Oxygen, which had been creeping up to 30 parts per million, dropped significantly when they tweaked the reboiler fraction.
And this is why instruments like the Carboscan are becoming essential, not just to prove compliance, but to tune the process.
But it's not the perfect picture. One big gap in the Twence trial was amines.
The chemicals used in the capture process itself.
That's exactly right. Amines are central to many post-combustion carbon capture systems, but online amine detection is still a technical challenge. Without it, the risk assessment for downstream use is incomplete.
And there's a growing concern, right, because we're talking about carbon dioxide that could end up in food and beverage products.
Yes, and as CO2 moves into markets where it's ingested or combusted, the bar for purity just keeps rising. We need instruments that detect ultra-trace contaminants, not just parts per million, but parts per billion and beyond.
So what's in the pipeline for ultra-trace monitoring?
Well, 2 technologies are getting most of the attention. Fourier transform infrared spectroscopy, FTIR, and optical feedback cavity-enhanced absorption spectroscopy, or OFCEAS.
Let's start with FTIR.
So FTIR is the more established tech. It uses broadband infrared to detect multiple gases at once, sulfur compounds, NOx, volatile organics, and it's already written into some European stack monitoring standards.
So it's regulatory friendly.
Yes, but its weakness is sensitivity. In a CO2-rich matrix, spectral overlap can mask impurities present at just a few parts per million or lower.
That's where OFCEAS comes in.
Yeah, so OFCEAS uses a laser in a low-pressure cavity, bouncing light thousands of times to achieve parts per billion sensitivity. It's especially strong in oxygen, carbon monoxide, methane, and trace sulfur species.
But it's not a generalist.
Yeah, no, OFCEAS is specialist, narrow in scope, but incredibly precise, and it's more expensive, so it's less widely deployed.
So if you're running a capture plant, do you pick FTIR or do you pick OFCEAS?
Well, I think that's probably the wrong question, because the answer is increasingly both. FTIR gives you broad coverage and regulatory reassurance. OFCEAS gives you the confidence that the handful of truly problematic contaminants are truly absent.
Well, that's great. Complementary, not competitive.
Exactly. Together, they provide the kind of data confidence that high-value markets, especially food, beverage, and synthetic fuels, are going to demand in the future.
So what should monitoring professionals take away from all of this?
So the first thing I'd say is that purity monitoring is now central to the credibility of carbon capture. It's not just about how much CO2 you catch, it's about what's in that CO2. Secondly, gas analyzers traditionally used in industrial gases are moving into capture plants. That opens up a new market for instrumentation suppliers. And lastly, the demand for innovation is real, especially in amine detection, aerosol characterization, and ultra-trace analysis.
And it sounds like data transparency will become a regulatory expectation, not just a value add.
Yeah, I think that's right. If the first phase of carbon capture was about scaling infrastructure, the next phase is about scaling trust in the monitoring. So that's everything we have time for this episode. If you want to dive deeper, check out www.EnvirotechOnline.com, where we've got expert interviews and presentation on FTIR, OFCEAS, and much, much more.
And don't forget to subscribe or follow wherever you get your podcasts.
Thanks for listening, everyone. Until next time.
Cheers, Chad. Bye from me.